السلام عليكم بسم الله الرحمن الرحيم رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني ويفقهوا قولي رب زدني علما. Today we are going to further continue with chapter 5. Uh, Now we are going to talk about the mass distribution on composite bodies. Now, if you take any composite body or a structure with irregular surfaces, what we can do is we can slice this body into small parts, and for each small part we can calculate its center of mass, and for that center of mass we can find the distance of the center of mass with respect to the global coordinate system, such as in this figure you can see this is a reference point. From reference point we are measuring for each centroid mass, and from there we are going to find out the overall center of mass of the entire body. And as you can see in this equation, we can add sum of the masses, sum of all masses, and the distance of individual mass, you can say this sliced mass, and divided by this total mass you can find the actual position of the x of the total mass. Now this is for one axis only. We can find this similarly for the mass distribution about y-axis and mass distribution along z-axis, and this is going to give us or provide us with the centroid of the mass. And now if the masses of the body is in composite, we can use the same technique. If the body is not composite, even then for large structures it can be used. The other technique is for the areas. Now we can use this thing again by taking a very thin slice of a cross-sectional area right here, delta x, and we can take this, and from this small slice of area we can find the center of this cross-sectional area. The smaller it is, the more uniform it will become, and the more uniform means you will have a precise position of the center along y-axis and center along x-axis. And once we add all these small slices together, we again find the exact value, or you can say the overall centroid along x coordinates and centroid position along y coordinate system. Now these two are the two approximation method. The first one we did it for in irregular surfaces, and then we talk about using a simple plane area. Now we're going to talk about volumes. In general way of volume is taking this volume and slice it into small cross-sectional areas, thin areas, and we can find for each area the centroid of that area, and based on the centroid of that area you can find, or you can develop a curve, the position of the centroid of that particular area defined here as xc. For instance, if you look at this figure, we have taken this volume and sliced it into many regions, and one of the region, let's say, is this small area. Now with a very small thickness, assuming delta x is very small. Now with this area we can find, as stated previously, you can find the value of x prime and y prime through this techniques established here. You can use the same technique and find the value of cx and correspondingly along x-axis from reference point where the centroid exists. And from there we can say for each mass or for each cross-sectional area we can find the value of their corresponding centers, and we have developed a specific curve based on that information. Now with this curve we found out the area under the curve will give you the center point of the volume, that is a dx. This will become you the small volume, that is dv. And from this dx we can find the value of the center position of the particular sliced volume. This is going to provide us with only x-axis, and we can find the position of this along other plots also. This is just for x-axis. We can do the same technique for y-axis and same technique for z-axis to find x prime, y prime, and z prime. For instance, now let's come to the simple sample problems. Here is the first technique. We need to find the here's the simple question, a small problem. Here we have to find the center of the area given in the figure. As you can see, this area consists of a square with 12 by 10, you can say a rectangle, 12 by not 12 but in fact 12 by 10 inches of height, and it has a semicircle that is subtracted from it, and a small rectangle which is also a subtraction of mass, and then a triangle. So we have four surfaces. Here we can find the area of each surface right here, that is 10 by 12, and then the positions, because it is symmetric, we can find the x prime and y prime of the entire surface, and we can find their corresponding x center along x, and the overall area as per the formula given before, and according to with respect to x-axis, and then we're going to find this volume position of a centroid of the area with respect to y-axis for the first part, then the second part, and then you can see the third and fourth part are negative signs because they are subtracted areas. And we can apply this information to our equations, and we will find the corresponding centroid of the given area along x-axis and along y-axis. Similarly, when we talk about a simple volume, and certain information is given here. As you can see in this particular problem, we have been given the initial position from 0 to 0.2, and here is the centroid for the slice at 0. It is at 2, and with 0.2 it is at 4, then 0.4 you have 5, then 6 means 0.6 means your area is near 5.2, then at 0.8 distance means the area is 5, and then you talk about 1, and then the area is at 4, and we take this information, and with this information we develop our charts. Now this movement from 0 to 0.2 shows the thickness of the slice. So for each thickness we are calculating the average area and this volume formation. From this volume formation we can find the x prime of that particular cross-sectional area, and we can find the volume times that particular sliced area's centroid. And we take this information for the total number of areas, and we can find the position of the center of the volume with respect to x-axis as given right here. As this information is right here, and this information is from right here. We can find the position of x prime. Now let's come to another problem. Now this problem is a three-dimensional problem. Previous two words, one-dimensional and two-dimensional. Now in three-dimensional problems you have different areas, different thin areas, such as you have a small region right here. You have this is a semicircle, then you have a square, then you have a triangle, and then you have another rectangle at the bottom plate, and then a cylinder passing through. Now you have these 5 volumes. Each volume has different, each region has its own weight. As you can see, look at the problem. This means the first vertical plate starting from semicircle to the bottom, before the bottom part, you have mass, the mass variation per unit area is 25 kilograms per meter square. Similarly, for horizontal plate is 40 kilogram per meter square. And finally, the center rod is 7.83 megagrams, that is about 783 tons, 7,830 tons per meter cube. This is the density. Now you can take this information and we can find the value of these plates along z-axis. Now if you look at this thing, he has placed the heaviest position at the origin, that is the cylinder. With this we can minimize a lot of things. Number one, since all the symmetric axes lie between along z-axis and on y-axis, the x-axis is eliminated naturally. So the location of the origin of coordinate is also very important. Now the first thing is to find the semicircle region, the region of the semicircle, the centroid of the semicircle, and this is the formula which is given in one of the appendices and addendum in appendix D. You can find the formulas for different shapes and their centroid positions. Now from here we have found out for this semicircle the centroid exists along z-axis at a height of 21.2 millimeters. Now for part 3, that is a triangle, you can see the triangular region has to be negative and the overall area has to be subtracted. So you have 150, that is the total height of the uh, from the origin to the bottom plate is 150 uh, millimeters. From there we have subtracted 25, and then 1/3, as we know the centroid exists at 1/3 the height of the triangle. As a result, we have found the centroid of this triangle to be from the origin at about 100 millimeter. For the other two, you can say the region 2 and region 4. Region 2 is a perfect square, and at the center of the square, that is 150 by 150 means 75 millimeter at depth is the center of the square, and the other one is along a y-axis, that is at the center of 100, that is 50 millimeters. And from there we can develop a simple table, as you can see, part 1, part 2, part 3, part 4, part 5, and here we have positioned for each mass cross-sectional area times masses, and we have found the mass of each part. Then we have to find the position or the centroid based on their axis. So we along y-axis we have found the bottom plate, and the cylindrical rod has the bottom plate, and the cylindrical rod has the centroids that exist along y-axis. And then we have along z-axis, since z-axis this way straight up, so we have found the value of the first part, second part, the third part is to be subtracted, that is a triangle, and then the fourth part along, since the fourth part is bottom far down the region, so we have to introduce that negative part also. So it is at a distance of 150 millimeter. From here we have found the value of masses along y-axis and mass distributions of each small segment along z-axis, and we have found the sum of my's and mz and the total mass. And we can use this equation, that is right here, to find the overall centroid along y-axis and overall centroid along z-axis. These are the few examples where we have learned how to find centroid of different homogeneous and non-homogeneous system. Like this example is considered to be non-homogeneous because we have different densities, and previous we have just a simple graphical representation of volume, and before that we had just a simple plane or an area. And all three examples shows how you can find the centroid. Now, one of the technique is these are all regions of different forms and shapes when you can understand there's solid inside. But what if we have a certain region, simple line, that is revolved about a center of axis to form a shell, or a certain cross-section area that has been revolved around a similar axis, about an axis to form a thick wall tube. So for that particular case, we are going to talk about the Pappus theorem. Now, he has the simple theorem is we can take a small slice of a ring or small slice of length L dl along a single chord from this is the chord which is shown. Now this chord is rotated about an x-axis. As a result, this forms a smooth ring, and we can find the area of this ring as presented here. We can say 2 pi, that is the rotation at which is about which it is going to rotate, the total 2 pi, and the value of y dl. Now y means height where it is located, and dl, this means initial value of y and final value of y. The internal area is going to be subtracted, and then you will be left with only the ring. Now it is a simple calculation to find the surface area and calculate the centroid of the surface area. Similarly, when we talk about volume, instead of using a line, we can use a cross-sectional area, that is dA. And you can use the same technique to find how this area is rotated about x-axis. In this case, we are going to get a volume. And for this particular volume, the only variation exists with dA. That is, ya is equal to the integral from y, we have the position of y, times dA, a small cross-sectional area that is rotating about x-axis. So with this, we came up with the expressions that is A defined as theta y L, where you have to remember the theta will be in radians, this means pi or 2 pi. And for volume again, theta ya. So for a simple area, your chord length is important, and simple volume, your area size matters. So we are going to talk about two examples here, and we can see in this particular example you have a simple torus, and we have to find the volume and surface area of the complete torus circle and its cross section. So simple, we have, remember, as we have studied before, it is just like a donut with a small area defined, a small r defined as a, and the distance from the center is capital R. So as we have studied before, v is equal to r, that is y is defined as r here. So we have just polar coordinate system, theta r prime a. So a, we all know, cross unit pi r square, that is small a, this is your a right here. R is the position from the center of the torus to the center of the cross-sectional area, that the circle area, and 2 pi is the rotation creates. So this is the volume we have got for our torus. Similarly, when you talk about the area, we know the surface cross-sectional area is this, that is 2 pi r, that is 2 pi a in this case, and for this area to rotate about z-axis we have 2 pi r again. So we have this equation 4 pi square ra. Now in the first case we found the volume, this means internal matter was considered, and the second case we just talk about the circumference of the area and how it moves around to form a shell. So it will give you the area of the torus. Now in next problem, we have to calculate the volume of the solid generated by revolving 60 millimeter, that is 60 millimeter right angle triangle area through 180 degrees. So we have a right angle triangle that is rotated about 180 degrees about z-axis. So considering it is still steel, what will be its mass? So we have to find the center of volume. So we need to know the area. The first area we know about the area is the area of this triangle, the cross-sectional triangle, this triangle. So we have found this area right here, 60 times 60 millimeters, that is half height into breadth. And then we have to find the radius. The radius is 30 plus 1/3 of the 60. Now why this small? 1/3 by 60. 1/3 by 60, we all know the center of a triangle exists at 1/3 of this distance. So from that center defines the rotational point. So we will find that r. And when we rotate this r, and then we form, so we know our rotation is of 180 degree, that is pi radians. So we have the information for our volume, we have the angle, we have the radius, and we have the cross-sectional area. As a result, we have found the volume of this region of this particular solid object. Now if you have to find the mass, so we have been told that this material is steel right here. So mass can be calculated density times volume, and we know the value of steel, we can find it from standard charts, and we put the value of density of steel, and we have calculated the volume, so we have found the mass of this particular steel. These are the few techniques to calculate the centroids of the structures. We can say centroid of different shapes, geometric figures, areas, and we are going to further study about different beams in upcoming structure systems. So before that, certain practices is required for you from your end. So please try to solve the end problems so you can have the expertise or experience in solving these problems. Thank you.